Alright, in this video we are starting homework 4 part A for separations, our final homework for this class. So in this one we are going to determine the degrees of freedom for a distillation column. We're going to go through each of the stages and pieces of it, so the equilibrium stage, feed stage, reboiler, condenser, the splitter, and a section of equilibrium stages in series. This is going to help us determine the degrees of freedom overall for a distillation column, and we will also talk about some of the typical column specifications for design and simulation that there are, and I'm going to get into that now. Alright, so we are going to start with the equilibrium stage first. So when I say the equilibrium stage, I guess I just mean one equilibrium stage. And that would look something like this. We have a temperature and a pressure. We have a vapor going up, a liquid coming in, and this would be something like that. If this is stage N, then this would be Vn. That would be Ln minus 1. And this V would be coming from N plus 1. And this liquid is Ln. Something we haven't really talked about is that there is heat transfer occurring. I'm just going to use Q as the heat, but there's heat transfer that can occur, around this stage. So the variables we have 4 times C plus 2 plus 3. So this is 4. There's 4 streams. C plus 2, C is the number of components. So if we had 4 components, we would put a 4 there and just do the math that way. But we're leaving it as C because we don't always know how many components we're going to have. The plus 2 is from the T and P within here, and this plus 3 is the temperature, pressure, and heat, that Q. So for the equilibrium stage, we have those variables. We have 4C plus 11. And then we can subtract what we know. So from the material balance, we have C equations. From the equilibrium, the thermal equilibrium that we know, there's C equations as well. And the energy balance gives us just one equation. And the temperature and pressure equality, that gives us 4 equations. So this gives us 2C plus 5. So to get our degrees of freedom, we take our 4C plus 11 and we subtract what we're restrained by. So we're restrained by our material balances, the equilibrium, the energy balances, and the temperature pressure equilibrium. So we need to subtract 2C plus 5, and that gives us 2C plus 6 for the equilibrium, for one equilibrium stage. Next, we can do, what was next was the feed stage. I'm trying to stay in the same order. So feed stage, again, trying to make this kind of look the same way as above. So we have, this time we have a feed going in. We still have those same flows. but now because of that feed, we have 5 streams. So we would have 5 times C plus 2. We still have the temperature, pressure, and heat transfer, so plus 3. And then instead of 4C plus 11, we get 5C plus 13. And the equations that we get from this one are actually the same as above, so I'm going to try to see if I can paste that. There we go. So that is actually the same for this one, which means we need to do 5C plus 13 and subtract the 2C plus 5 to get 3C plus 8. And that is the degrees of freedom for a feed stage in our column. And next we wanted to do the reboiler. So the reboiler, if we remember, is something like this. We have a liquid going down into it. We're sending vapor back up, but we also take out the bottoms. So this time we only have 3 streams instead of 5 or 4. So we have 3 streams times C plus 2 again. It's always times that C plus 2. And we still have the TP and Q, so we have the plus 3. So this time it's 3C plus 9. So I'm not going to rewrite it, but this is the same as above, so we have 2C plus 5 already defined, and we need to subtract that from our 3C plus 9. And then we get C plus 4. And that C plus 4 is for our reboiler. So for example, if you had a 2-component system, then your degrees of freedom for a reboiler would be 2 plus 4. So you would have 6 degrees of freedom, which means you could define 6 things basically. Obviously the more components you have, the more degrees of freedom you'll have, but generally you're restrained regardless. So we did the equilibrium stage, the feed stage, the reboiler. Now we need to do our condenser. And remember that this is a total condenser. So we are completely condensing all of the vapor that goes into that condenser. We have a vapor going into our condenser, and we have liquid leaving. That goes into the splitter, which we'll talk about next, where we have our reflux coming back into the column, and then we have coming out is our distillate, but what we're focused on is we are focused on this section. So as you can see, we only have 2 flows, which means we do 2 times C plus 2. Because of us completely condensing all of the liquid, we no longer have this same C equations from an equilibrium, because we just have one type of phase entering and one type of phase leaving. So from the material balance, we have C equations still. That always holds true. Our energy balance again is one equation, and this time we have a temperature and pressure that gives us 2. So we get from this one, we only get C plus 3. And this is good down here, but I got sidetracked by it being different and forgot to add our TPQ. So we need to do 2C plus 7 and subtract C plus 3, and that gives us C plus 4 for our condenser degrees of freedom. And remember, this is a total condenser, but I'm just going to write condenser. And so we did the condenser, and now we need to talk about the splitter. I'm not going to draw the splitter because it's kind of above here. But yeah, the splitter has 3 flows. It has a flow going in and 2 flows coming out. So it is 3 times C plus 2. And we still have the plus 3 from the T, P, and Q. From the material balance, we have C equations still. The energy balance is 1 equation. Again, we can't say that we have anything from the equilibrium because it's all liquid phase. And the TP equilibrium gives us 4. And since it's the same component, we need to do C minus 1. So that gives us C plus 1 minus 1 plus 4. So we get 2C plus 4. And up here we had 3C plus 9. So if we do 3C plus 9 and subtract the 2C plus 4, you get C plus 5 for the splitter. And now we have done most of it, but we also want to do multiple stages. We said that one stage over here was 2C plus 6, and n stages we would have n times 2C plus 6. However, we need to subtract the duplicate streams. So we're subtracting 2 times n minus 1 times C plus 2. And we need to add 1 because this is the degrees of freedom for any number of stages that we need to add, just inherently. And so what we get is 2n plus 2c plus 5. And that is for n stages in series. So that would look something like this, where these rectangles are stages and you have the vapor flows and liquid flows between them. And now we want to do the column overall degrees of freedom analysis. So we have 2n strip, that is the number of stages in the stripping section, plus 2, so this is from above, plus 2c, plus 5. This is the stripping section. And we need to also have the rectifying section. Our feed stage was 3C plus 8. That's our feed. Our reboiler was C+4. The total condenser was the same, and the splitter was C+5, I believe. So this was our condenser and splitter. And adding that all together, we are left with 2 times N strip, so I'll just use an S, plus NR for the rectifying stages, plus 10 C's, plus 31. So as long as you know your number of components, the number of stripping stages and the number of rectifying stages, you could calculate this. But we're not done yet because we need to subtract the double counted stages. Or, sorry, not the double counted stages, the double counted streams. Because we, as you can see, have streams that we're double counting. And that is 9 times C plus 2. So after we subtract 9C and 18, we are left with 2NS plus 2NR plus C plus 13. And this is our degrees of freedom for column overall. So for example, let's say our number of stripping sections is 5 and our number of rectifying sections is the same. And let's say we have a 2-component system, and then we would have 2 times 5 plus 2 times 5 plus 2 plus 13, and that is 35 degrees of freedom for that example. Now, talking about what we could specify, if we were to specify, for example, if we specified the Q and the heat and pressure for each equilibrium stage, that subtracts our that subtracts our 2NS and NR. So then we're actually left with C plus 13 degrees of freedom just after one specification. If you specify the Q, T, and P for the feed stage, what you end up doing is you subtract a C plus 2, so we're left with only 11 degrees of freedom. If we define the pressure for the reboiler, condenser, and the splitter, that subtracts 3. And then we are left with 8 degrees of freedom. If we say the divider is adiabatic, then we subtract 1 and we get 7 degrees of freedom. And I should say that this specification up here was for the feed, like the feed flow, so the feed going in. But we can also specify the feed stage Q and P, which the feed stage is different from the equilibrium stages, so it's not accounted for there. So that subtracts 2, and we're left with 5, and you can just keep going. Some design specs that would work as well would be to define the number of stripping stages that you have, and then you could also define the number of rectifying stages that you have. That would constrain your system. You can also define the distillate flow rate, so how much distillate you are taking out, and you can also do the reflux ratio. And then, so we wanted to talk about the design, so that's the component separations specified, but we also want to see what we could do for the simulation. For the simulation, we could do the light key recovery, or if you have a two-component system, the recovery of your more volatile component. And you could also specify your heavy key recovery. You could also specify where your optimal feed stage is. And then again, you can do the reflux ratio. Thanks for watching. That video went a lot faster than most of them, so I might have missed some things, but hopefully that made sense. And so for homework 4, for separations, we only have one more part, which is part B, and in that we're going to simulate the dynamic response of a 7-stage distillation column with a total condenser and reboiler. And we have some other considerations, but overall, that's what we're going to be doing. Thank you for watching, and stay tuned.